All right, good morning, everyone. Welcome to the DMSC QIF Coffee Chat series. This morning, we've got Tom Groff and Colby Finn from QBI OGP, and they're going to be giving a presentation talking about how to better your efficiency through QIF. Why don't we, before we get started, we should take a look at our housekeeping slide here. We have a couple housekeeping issues we'd like to talk about. Basically, on your screens on the right-hand side, you'll find that there's a place to type in your questions. And we'll save all these questions until the end, although you can put your questions in at any time during the session. And I'll be moderating the questions at the end of the session. Also, it's important to know that everyone that is attending the session today will get a copy of this video, which is obviously being recorded, and that video will show up in your inbox tomorrow. So why don't we go ahead and get started? We have Colby and Tom from QBI OGP. Thank you.
Thanks, Mark.
Thanks, Mark. So today we're going to share some examples of how software packages are leveraging the QIF standard to make the quality function and manufacturing in general more efficient. So we're going to cover a little background on the QIF standard itself, and then demonstrate technology that exists in software products today that helps manufacturers save time and money. So we'll conclude with some details on where we see this technology going in the future that will even further increase productivity in both metrology and manufacturing. So Tom and I work for Quality Vision International, the company that designs and manufactures technology sold under the Optical Gauging Products, or OGP brand. So OGP offers multi-sensor measurement systems and software for dimensional quality control. OGP's most well-known product is the SmartScope, a video multi-sensor measuring machine. You can see one of our benchtop models over here, pictured here on the left. But we make many other measurement systems, including CMMs, optical comparators, shaft measurement systems, and 3D laser scanning systems. What's unique about our company is we design and manufacturing just about everything needed for non-contact measurement, meaning we design and build the transports, we design the lenses and illumination for video measurement, the various other sensors used for measurement, and the measurement software, both for operating our systems and analyzing data from various measurement devices. So at OGP, we celebrated our 75th anniversary last year. An important part of our history is innovation in software. So when OGP first got into the quality control business, all measurements were taken with the human eye, with tools like this optical comparator you're seeing over here on the left. And today, it's hard to find any piece of dimensional measurement equipment that does not require software to take a measurement. So this transformation occurred in optical measurement because software made metrology easier and more cost-effective. So when as a company, we started branching out from just optical measurement to more of multi-sensor measurement that deals with points from all different types of technology, we decided to focus on what else we can do with software to make things easier for our customers and reduce the amount of time they spend programming measurement machines and trying to analyze the output from these measurement machines. So this is where QIF comes in. We decided to leverage the QIF standard to make metrology faster, better, and easier. So what is QIF? It stands for Quality Information Framework. It's an XML-based, CAD-neutral, free standard used to communicate quality information throughout an organization. So by quality information, I mean measurement results, part nominals and tolerances, measurement plans, measurement strategies. The fact that it's CAD neutral and based on XML makes it great for interoperability between different proprietary software packages, but also between people and computers. Since XML is human readable, you can easily interpret what's in the standard. So QIF is key to enabling the creation of a model-based enterprise where information flows digitally and efficiently between different functional groups in an organization, all traceable back to the CAD Digital Authority. So the QIF standard is all about easily sharing information without compromising that data integrity. So QIF is developed and supported by the DMSC, the Digital Metrology Standards Consortium. So if you want more information on the technical details or its implementation, contact the DMSC or you can visit their website. So we're going to show a few software demos of OGP's Evolve suite. Evolve is a suite of model-based software packages designed to reduce waste of time and material in manufacturing. So we do this with a focus on communicating product tolerances across the enterprise. Geometric tolerancing, or GD&T, is very effective when used across an entire manufacturing organization properly and consistently. But unfortunately, this usually is not the case in today's manufacturing companies. For example, maybe the design engineer does not apply the GD&T properly per the standard, or doesn't add the tolerances to the 3D CAD model in a way that can be used downstream in inspection. On the other side, sometimes production engineers don't know the best way to adjust their machining process when quality gives them their GD&T results. Production engineers want to work in their manufacturing coordinate systems and adjust their fixtures and their tool offsets, as opposed to working with and analyzing a complex GD&T datum structure. So all the Evolve software products are connected through the model using QIF, and each product targets a specific functional group, meaning design, engineering, inspection, or manufacturing, to solve their problems with GD&T. So since they're all connected through the model in QIF, this allows objective and digital communication throughout the organization. And therefore, a company can realize the full benefits of GD&T. So we're going to show you 4 short software demos that use QIF to make manufacturing more efficient. First, about objectively communicating design intent, automatically creating measurement programs, maintaining traceability, and enabling root cause analysis of tolerance failures. So first, we'll focus on communicating design intent. So I'm going to show you the design module of Evolve, where the software takes in QIF files and exports out in QIF format to help set up and validate GD&T, so the part's ready to be manufactured and inspected. So I'm actually going to show 2 different use cases. One where the quality engineer is performing this GD&T proofing and validation, and the other where the design engineer is the primary user of the software. Either use case may be appropriate for your company. It depends on how far along you are in your transition to being a model-based enterprise. So this first use case is a quality engineer receiving a QIF file from design engineering that contains both the model and the tolerances digitally. But just because the tolerance information is there doesn't mean it's correct per the GD&T standard. It's not necessarily that the design engineer did anything wrong, but perhaps they did it in a format that cannot be understood properly by computers and downstream applications. So this is Evolve Design, and the first thing I'm going to do is import a QIF file. So before I load it into the software, I'm going to open it in Notepad so you can see the format. So you can see it's an XML file. It follows a certain standard format, but it's human readable and easy to interpret. So now I'm going to bring it into the software where you'll see the QIF has both the CAD model and the GD&T callouts built in. So on the right side, you will see a tolerance proofing panel that highlights tolerancing errors, GD&T standard violations, and warnings. So the purpose of this software isn't just to tell you what is wrong with your GD&T, but also help you fix the issues. So the first thing it's saying is wrong is that I have a perpendicularity callout, but it doesn't reference the datum. So I can click on my callout here and edit it. In my edit window, I have an explanation panel on the left, and this will point me to the exact place in the GD&T standard where this tolerance type is described. So if I'm confused on why the software is saying it's incorrect, I can open the standard and see the text and diagrams directly. So when I open the standard, you'll see in specifying orientation tolerances, it explicitly says the considered features shall be related to one or more datums. So I'm going to add a datum to my feature control frame and the error will go away. So next, the software is going to highlight that I have a standard violation on a position tolerance. So here it's saying I need to apply a size tolerance to the feature or remove the material condition modifier. So I'm going to remove the modifier and the error is going to go away. So in addition to correcting tolerances that were already in the QIF file, you can add your own in the design module. Say the designer did not put 3D PMI in the model. So I'm going to add a profile tolerance to this feature here. So while I'm editing the feature, you will see I have the ability to assign a measurement strategy. This is to define how the feature should be measured in inspection, what tool to use, what point sampling and filtering, etc. And in the next demo, you'll see how this information is used downstream in metrology, to actually measure the part. So I'm going to add a profile tolerance to this feature. And again, I have that explanatory system where I can actually view the standard if I want more information on a profile tolerance and the different modifiers that can be used. And once I'm finished proofing and adding tolerances, I can export the QIF file for downstream use in the metrology lab. And this is the first use case for the quality engineer. The second is more appropriate for a design engineer. So in the next use case, instead of pushing the corrected tolerances downstream for use in inspection, we're going to push them upstream back into the CAD package. So if your company is fully committed to becoming a model-based enterprise, this is what you're going to want to do. You want your CAD file to be the digital authority and ultimately contain all the correct information. So in this use case, I have two windows open, the actual CAD software on the left, in this case, PTC Creo, and Evolve Design on the right. So instead of importing tolerances from a file, I'm going to sync directly with the CAD package to grab the nominals and tolerances. But you have the same functionality you saw in the previous demo where I can correct and add tolerances. But when we're all done, instead of exporting to a QIF file, I'm going to send the changes back up to the CAD Digital Authority. So here I'm going to correct the position tolerance. And I'm going to delete one of the callouts that came in from Creo because it's not appropriate and add a profile tolerance instead. And now I'm going to click a button in design and it'll send all those changes back up to Creo and you'll see them appear over on the left. The flatness will go away and a profile tolerance will appear on that cylinder. So what you just saw was a way to use QIF to communicate design intent and create efficiency by reducing redundant operator input. So if the design engineer has already input tolerances and DRFs into the digital model, the quality engineer doesn't have to redo that work. And second, you can prevent downstream errors by correcting tolerancing errors early on in the process before the parts get made or inspected. So our next software demonstration will take a QIF file and automatically generate a measurement program to acquire the appropriate data points on your part to evaluate the GD&T. So I'm going to show you Zone 3 software. This is the executive software that operates our OGP multi-sensor systems. But for reference, we also offer an I++ client if you want to run Zone 3 on other vendors' equipment, and other metrology software vendors also support the input of QIF files. So the first thing I'm going to do is import a QIF file into Zone 3 that has the CAD and the tolerances. And the software knows which critical features need to be measured based on the GD&T in the QIF. And right here, you can see there's a checkbox where I can tell the software to only measure what is needed to evaluate the GD&T and not input all the rest of the features. So now it's going to tell me it found tolerances and features in the file and ask if I want to create a measurement routine. So this window that popped up here, it's showing the features it found in the QF file and how to measure them. So it's called a step template in Zone 3, but here's where the measurement strategy is stored that came over from the QIF file. And again, by measurement strategy, I mean which sensor to use, what point sampling to take, what filtering to do. And in this interface, I can see what automatically came in from QIF, like it's saying to measure this plane with a laser, measure this second plane with a touch probe. And I can either change the strategy, modify it, or accept it. So when I'm done looking at the measurement strategies, I can hit generate and it will create the measurement program automatically. All right, so now I am ready to run the routine. And I'm gonna turn on the machine so you can see what's going on. Obviously, this is an offline simulation. So I got a multi-sensor machine here with a video sensor, scanning probe, and a through the lens laser. So right now it's measuring the part with the laser. And I'm gonna zoom in here so you can see what it's doing with the probe. And again, these measurement strategies and which sensors to use all came in from the QIF file. The person operating the measurement machine did not have to select them or program them. All right, and what you saw in this demo was that you can use QIF to create efficiency by automatically programming measurement machines. So this saves you time and money because the operator of your CMM or other measurement machine doesn't need to input the nominals, tolerances, sensors, or paths, and you can have a less skilled operator running your measurement system. So the two big goals of the QIF standard are to create interoperability and traceability. So the previous two demos focused on interoperability. So this next demo will highlight the aspect of traceability. And by traceability, I'm specifically referring to the ability to access the appropriate data if something goes wrong with the part or something changes. So QIF has this concept of a QPID, or a persistent identifier, that can be tied to a measurement characteristic for traceability. So obviously any company can come up with their own convention for traceability, but with QIF being an open standard, your entire supply chain can be using the same language and conventions to maintain these connections throughout the product lifecycle. So I'm going to show the evaluation module of Evolve, which takes in points from any device, any measurement device, a CMM, a 3D scanner, and fits the points to a CAD model to evaluate the tolerance and give you measurement results. So here we're starting with a QIF file, which already has the CAD model and the tolerances, and I just input the points from my measurement device. So now I'm going to click evaluate. So we'll do that fitting to the model and produce results. So my tolerance is passed, my GD&T passed. I can see the callouts in the model. You can see the points on the model. And I have the detailed results on the side. So now that I have the results, I can output to a QIF file, which will send both the results and the measurement points to a QIF file, okay? And typically this whole process is automated, where as soon as a point file is generated, it's dropped in and evaluated and output, meaning there isn't someone here clicking manually doing these operations. So say we have a production engineer monitoring the measurement results of these parts with control charts, and say one of the features hits a control limit. So I can look at this feature, it's circle D6, the form of circle D6, and go to my analysis tab to see the metadata associated with this feature. So I want to click on that circle D6. I can see where in the CAD model that feature was measured, and I can see stats on the part or on the feature and also which part it conforms to. So in that previous screen, I saw it was from part 139. So once I've identified the part and the characteristic, I'm going to come back to the evaluation module. So because I export to QIF, I can now bring that QIF file back in from that part that hit the control limit. So this is the concept of a digital twin in model-based enterprises, where the part data can be brought back in to be reanalyzed in the future. So here I input the QIF file for the part that failed that contained the points. And I'm going to reanalyze the results. Specifically, I'm going to look at that cylinder and see if I notice anything off that needs adjustment. So again, I'm going to pick that feature that was failing in my control charts and see if I notice anything off. So the key here is that both results and points are stored in an open but traceable format in QIF, so they can be identified and recalled anytime, anywhere throughout the supply chain. And that's how you use the QIF to really maintain this traceability.
Make a quick point, Colby. So just that QIF output can be a single file, it can be multiple files, it can be files over at different plants. That's the beauty of the framework, is that those files can reside anywhere and they're all connected via this Cupid, each of the features or the machine that it's using, whatever, is connected through this unique identifier. And that's how you can dive down into that data. I'm going to talk about that a little bit in my future growth part also.
Thanks, Tom. So this last demo was about root cause analysis. So we're going to go a little bit deeper into the analysis of measurement data to figure out what to do if your GD&T is failing. So we're going to start out with a QIF file that has the nominals, the tolerances, and the measurement results in it. And the first thing we're going to do is evaluate the GD&T results. And I have a bunch of failures on this part. So I'm going to pick one of them. I'm going to look at a specific run out call out. And if I click on this total run out tolerance, I can see the points associated to it. This little animation over here showing me how it's constrained by the datum, in this case, datum C. If I didn't understand the call out, I have that explanation panel we looked out earlier. See that context sensitive explanation, images of the standard. But say I know what total runout is, but I'm not sure why this feature is failing. Was it machined in the wrong place, or is that Datum C wrong? And that's what this software is going to answer for me. So I'm going to go over to the manufacturing module of Evolve and either import from a CAM file or manually enter my manufacturing information, meaning my machining coordinate systems, and tell it what groups of features were machined together. So with the manufacturing information in the software, we can run what if simulations on the GD&T results, meaning what if I shift manufacturing operation by 1 over by a given amount, or if I change a tool offset, would that make the GD&T pass? So now we're going to go into the simulation wizard and I'll show you that here. So you have to tell the software which operation or list of operations you want to optimize. So here I'm going to select operation 1, that operation that cut those cylinders that form Datum C, and tell it can translate it in X and Y. So when it's done, it will come up with a recommendation for how much to translate that operation. And it will also show me my actual GD&T results and then what the simulated results would be with this correction added into the manufacturing process. So over here on the left, you can see, it should highlight it in a second, that it came up with an offset in both X and Y, about 0.1 millimeters in each. And then in the model window, you'll see those before and after results I was referring to. To the left of the arrow is before, the actual measurement points, and to the right is the simulated results after correction. And you can see this runout call out I was analyzing actually passes with the suggested adjustment. So on the right, you can see the GD&T results from the entire part, and actually everything passes now. So that Datum C was the whole problem and what needed to be adjusted.
So another quick comment, Colby. So for those of you that might not have caught it, there's a mapping between the functional datums, which are related to the GD&T callouts that define a good or bad part, and the operational datums that define how to manufacture the part. And that's what's unique about this software is it knows where those are mapped together, so that when I change these manufacturing datums, it is affecting my GD&T results either in a positive or negative way. And it has that optimization tool to define how to change those so that I can get either passing results or as close to passing as I can with the limitations that I have. So that's the key there is you got the mapping of the two coordinate systems together.
Right. So like Tom just said, that QIF file is critical to really connecting the quality and manufacturing functions through their coordinate systems. And the key here is the production engineers have access to the measurement data and results in a form they can use. They don't have to re-input the tolerances, the functional DRFs, because it's there in the QIF file. So because of the sharing of data between quality and manufacturing, the measurement machine or the CMM utilization can be solely for measuring parts and not performing this advanced analysis that's better done offline, say at an engineer's desk. So that's it for the 4 examples of how QIF is being used today. And now I'm going to turn it over to Tom to provide some insight on the future of QIF and where we see model-based enterprises going with the technology.
Thanks, Colby. So yeah, I think it's important to distinguish, the MB, the model-based enterprise vision that we all have about how machines and software can communicate together and make manufacturing much more efficient and better quality, and the current reality of model-based enterprise. So what Colby was showing you is the reality today. That's what we can do with software to assist manufacturers in making better parts and being more efficient, better quality, all that kind of stuff. But really, there's credit to DMSC for creating the standard that allowed us to do this through a common framework, right? But also credit that it is very intended to handle the growth that can happen. And that's what I'm going to talk about, the future of QIF and how it's going to affect model-based enterprise. So it's allowing us to do what Colby said, and it's also allowing us to do some future things. And the areas that I see growth there are in smart software, intelligence, applying intelligence to machines, and making it so that the user knowledge is not so important and fraught with error. Also the analysis side, taking big data from multiple factories and understanding it and making good business decisions from it. Related to the digital authority model, having a single authority and its derivatives be all synced together so that they're all communicating to each other and not out of sync. And of course, collaboration is key. Everybody has their own expertise, and collaborating is how we get together, both from manufacturers, suppliers, education. All of these different disciplines need to collaborate together. So I think the first, relative to intelligence, the area of most growth there is related to how we can take that information that is in the QIF file and apply it. So information that can reside in the QIF file is, of course, the part tolerances, which you've seen already, the part data, measurement data, but also things related to how you're measuring. So the machine uncertainty can be known, the sensor uncertainty can be known, and when we know all of this information together, we can make the software more intelligent. It can make decisions on what is the most appropriate machine to measure this part, what is the most appropriate sensor to measure this particular feature and this tolerance, knowing that I have a touch probe and a laser and a video machine on my multi-sensor system. What one's most appropriate? What's going to be fastest and still maintain the accuracy that I need for that tolerance? It also can help automate your sensor strategy. So how am I going to measure it? How many touch points am I going to do, or what's my laser scan path going to be looking like? And the point density, how many points do you take on a feature to effectively characterize it? So all of these things are related to intelligence. Right now, users make most of those decisions. Mostly programmers of automated inspection machines make these decisions. And sometimes they're right and sometimes they're wrong. You need to have pretty good knowledge to know how to do all these things. Not necessary if you have the information in QIF. So when you think about that from a multi-part perspective, and you're measuring statistical information now on many parts, you have that statistical information can be used to provide intelligence too. So if I find that over multiple parts, a particular feature is very stable, I might not need to measure it every time. I might just need to measure the critical features or the risky features, the features that aren't stable, and I can dynamically adjust my measurement strategy via QIF to define, what to measure. But I can also define how to measure it. So if I know that I need to take more points for it to be a more stable feature, I can adjust the how to measure it. And also part to part, if you're finding that the part is very stable and maintaining all the control limits, you might sample the part less. So instead of measuring every part, I'm measuring every 10 or 100 parts. This kind of intelligence is what I'm talking about. A lot of growth potential here to make machines smarter. It's about balancing throughput, costs, efficiency, all that stuff. So taking that data, the analysis part of it, again, that what I referred to earlier with that quality persistent ID that's in the QIF file, the QPID, that unique identifier allows analysis of data and allows you to drill down into that data that might be from multiple factories or multiple machines or multiple operators, and find out where the issues are and how I can become more efficient, or how I can measure the part without it going out of control. So a lot of growth area there for understanding how to make good business decisions from that data. Another thing I want to touch on was statistics in GD&T. When I'm taking lots of data on the same part, and you apply GD&T tolerances to it, I might have bonus tolerances. These tolerances become variable, and so having a good statistical package that understands that and can react and provide the correct feedback to the manufacturing tools like Colby was showing is important. So instead of just a static, traditional tolerancing, GD&T tolerancing can be pretty complex and variable, and so it's important to be able to use that to make very efficient and correct manufacturing operations. And the last area I think is the relative to the digital authority model. That is the key to model-based enterprise, having a model that has all of the correct information for upstream and downstream operations. But the CAD packages are typically where that digital authority model resides. But there's a lot of connections to that, including what you saw here in the measurement program as an example of what we call a derivative model. So a derivative is something that is based on that digital authority model, but has extra information in it. And most of that extra information can reside in the QIF in the QIF framework. So the key there is mapping all of these derivative models or derivatives from the model to the digital authority model. So when a tolerance changes or the part changes, that all of those derivatives get triggered to change also, otherwise you get out of sync. So there's a lot of growth area there to have these software packages communicating to each other to say, okay, there's a change, let these other 10 software packages know there's a change, and either hopefully automatically make that change, or at least trigger them to make that adjustment and stay in sync, and allow checking in for those changes to the digital authority model as well. So I see a lot of growth in that area. So, and I think in general, a lot of growth in further collaboration. We've collaborated with CAD companies. We've collaborated with semantic correction companies like CAPvidia. They have their subject matter expert is maintaining this digital connection and semantic information within the CAD and QIF file to have upstream and downstream operations being communicated. So we've been working with them. We've been working with CAD companies. We work with machine controllers to know how to adjust machine tool offsets. And we're just one part of the QIF network. A lot of different manufacturers, OEMs, suppliers are contributing to this QIF data. The richer that data gets, the more useful it will be. And so, we need to support those other contributions where that data is getting richer. And if we can use it in our own world, then it will enable manufacturers to be more efficient and more effective. So collaboration in this, model-based enterprise world is key for sure.
And that's all we had today for our presentation material. So Mark, if you want to open it up for any questions from the audience.
Yep, absolutely. Thank you for that. So we do have some questions here in the queue. So let's just take a look here. First question, what software do you use for your 3D models, and which ones are you using to transfer your models into QIF format?
I'll take that. So the model is, like I said, there's typically a digital authority model from a CAD package like Creo or SolidWorks or something where the PMI is defined. If that PMI is not defined within the model, different companies aren't putting that into the model necessarily, then that information can come from, what Colby showed in our design module, where you can author that PMI information, put GD&T on that model so that it is complete and usable. So there's different scenarios. I think the model can come from the digital authority, like a CAD package, if it's got that PMI information in it. The digital authority could be the design package if the CAD is not populated with PMI information. So it can come from multiple sources, depending on how much a particular company is embedded in MB and whether their models have that information or not.
All right, great. Thank you for that. Next question. Does the Evolve Design Suite work with Inventor as well? And I assume that's the Autodesk Inventor.
Yeah. So Autodesk actually outputs QIF directly. This is new in their 2022 version, which just came out in November. But so yes, they support QIF files straight from their software, and that can be used to bring into the Evolve suite.
You can bring QIF into the Metrology package that runs the machine, or this evaluation package, the Metrology Suite Designer or Smart Profile. And you can bring in QIF and even native models directly into those packages. The only bridge that we have that Colby is showing is with Creo right now to feed that back upstream. So if we correct PMI and need to get it back upstream, the Creo is where we have that bridge.
All right, very well. Next question, is there a preferred neutral CAD format? Is the design module able to update the native CAD file as well?
Yes, so the preferred neutral CAD format for us is QIF. Obviously, well, not obviously, but there's step AP242 as well. But QIF allows you, like Tom explained, to associate that additional information that can be used in metrology and manufacturing. It has that really flexible framework that allows these derivative models and derivative products to work with it. And like I did show it in the demo. The second question was about, can you repeat the second question? It was about pushing the QIF, pushing the tolerances back up to CAD, Mark?
Yes.
Yeah, so that is possible. Like I showed in the demo, just with PTC Creo, that bridge that we mentioned can push the corrections back up to the CAD package. And otherwise, it will just export the corrections either in a report-like format or in QIF format that can be then manually added back into the CAD package. But that bridge functionality where it happens automatically is available for PTC Creo.
All right, so this is a somewhat related question. For those interested in managing a QIF validated document as part of quality control in a workflow, to capture the information about variability in process, any thoughts or comments on software for viewing and editing the document, or will any XML editor suffice?
So typically people, don't create XML documents, right? And so there's software that is either authoring it or correct or changing it. And that's what most of our software packages are. There's kind of the user interface in front of it that allows you to make the adjustments in an understandable way to populate or change that XML file. And I think that's preferred from people that want to use this stuff. And so the CAD companies, companies like us that run metrology equipment and analysis software, that's kind of how the XML files are adjusted. But for viewing the XML files, there are common methods of understanding that if you're kind of a coder and need to get down into the detail and do some manual manipulation.
Right, understand. All right, next question is, can the software automatically optimize machine offsets to minimize the out of tolerance parts?
Yes, so that's what the manufacturing software is designed to do. Essentially, you can have it runs a bunch of Monte Carlo simulations on different machine offsets that will then evaluates the GD&T results to see what's the ideal adjustment to give passing or results.
All right, and another related question is, how are tool offsets calculated? Statistical data or single point? And can outliers be removed prior to calculation?
So currently, the manufacturing module that Colby showed is taking a single sample of data and doing those Monte Carlo simulations to optimize the results. We do have a statistical package that's connected to both the design and the manufacturing module. So multi-part data is collected into a database and can also be stored into the QIF framework. Those simulations currently are not multi-part, but that is in one of our immediate roadmaps is to kind of combine our statistical package and our manufacturing package so that multi-run data can be used for the kind of simulation and GD&T optimization.
Very good. All right, next question is, the standard shown in the example was Y14.5-2009. Is there an ability to select which version of the standard is used for checking validity of GD&T?
Yes, you can readily change the project as well. We support 1994, 2018 as well, and also the ISO standards for tolerancing. So yes, you can select which standard you want your project to be evaluated against.
All right, perfect answer. Does the analysis extend to assemblies of parts?
At this point, no. We're focused on single parts for doing that manufacturing analysis of how to correct your machining process. So anything you want to do with assembly, you'd have to post-process based on the results.
Great. So how are the simulations performed in the software connected back to the CAD models?
Through fitting and Monte Carlo simulation, would you say, is that an appropriate answer, Tom? I'm not exactly sure I understand the question of how the simulations are performed.
Yeah, I think there's maybe a disconnect there. So the simulations are performed within design, and the corrected out offsets are provided to the user. That doesn't end up going back to the CAD model because there's nothing to change there. That goes downstream to the manufacturing process. So the CAD model is still retained. Yeah. There's no changes after a manufacturing simulation.
All right, thank you for that. Next question is, how difficult is it to populate measurement rules and gauging in the involved software?
So right now, the rules are just essentially a name. So the populating, the setting of the strategy is done in the metrology package, in our case, zone 3. In Evolve, we just call the certain template. We assign each feature with a certain template. So in the future, like Tom has talked about, we have plans to make more intelligent ways embedded inside of Evolve to plan that measurement strategy automatically. But right now, you're just assigning the name of a strategy inside of Evolve.
Yeah, it's an interesting concept in programming of a metrology machine. The way that people have programmed a CMM or a video inspection machine has been you look at a print and you say, okay, I need to measure that, and so I go and manually measure a datum, and then I just measure that particular feature and report it. And so now with this kind of MBE concept, the method of programming is much different. You're really defining what we call templates. If I need to measure a cylinder, I want to measure it this way, and I, the CMM programmer, am defining how to measure it, a single feature. And so it's much simpler, and you don't have to have as much knowledge. And what the measurement program and the sequence of how you measure it so that you're compliant to the standard and in the most efficient sequence and all that stuff, you don't need to do anymore. All you need to do is define, how to measure a particular feature, and then those templates can be defined by the designer. So like Colby did, she said, measure the cylinder with this template. And then when it was brought into the measurement package, it knew, okay, well, I'm going to measure it with this template. The template was defined by a programmer at this point. At some point, what I was speaking of is that even that part of it can be automated so that the programmer doesn't have to program those templates anymore, but that's not here yet.
All right, got that. Last question here. Can the code exiting from OGP software, can that be handled by a Zeiss CMM?
If we're talking about running a measurement machine to collect data points, then yes. So OGP's Zone 3 software can operate as an I++ client, and Zeiss offers an I++ server. So those two things together allow you to run Zone 3, the interface that I demonstrated on a Zeiss CMM.
All right, so I would have to say that you guys did a great job answering those questions. We did have quite a few questions, so clearly our audience was very well engaged. So appreciate your effort here, and I hope that our audience found this session to be very informative. I know I learned a lot, and I would hope that everyone else that was here for that purpose did the same. So that's going to conclude our coffee chat sessions for 2021. This is our last one, and we are setting up a program for 2022. We hope that if you enjoyed this session that you'll be back for more of our sessions, and who knows, we might get Colby and Tom back again to talk perhaps on a slightly different subject. Of course, all focused on QIF. So everyone, thank you very much. Colby, Tom, thank you, and everyone that attended today, we appreciate it. And don't forget, you'll be getting a copy of this video in your email tomorrow. All right, everyone, thank you.
Appreciate it, Mark. Thanks to you and the DMSC for sponsoring the webinar, and thanks for everybody for attending. Any questions, feel free to ping me or Colby on it.
Fantastic.
Thanks.
All right, thanks, everyone.
Bye.